Hello everyone. Today we will discuss on an important topic of fiber optics. The name of the topic is numerical aperture and acceptance angle. In previous lectures, we have studied basic concepts and fundamentals of uh, optics and optical communication system. The fundamentals which are required so that light signal propagates inside the cable. So in that continuation, today we are going to talk about numerical aperture and acceptance angle. As we can see, the definition of numerical aperture, it's a measure of or measure for angular acceptance for incoming light and defined, and numerical aperture is defined based on geometric considerations. The geometric considerations of the material are considered. What do we mean by geometric considerations? We'll see in the derivation of numerical aperture, but it is the measure of angular acceptance. That is, how much is the span of angle where light enters and will undergo TIR inside the cable. That acceptance angle is correlated with numerical aperture. So numerical aperture, in other words, it's measure of that maximum acceptance. This is a theoretical parameter which is calculated from optical design and cannot be directly measured. Optical design means what are the different materials, what are the refractive indices, what are design factors and parameters. Those are considered, their refractive indices and other parameters in estimating the parameter, that is numerical aperture. This is defined as a product of refractive index of the beam which the light input is received and the sign of maximum ray angle against the axis for which light can be transmitted through the system. Look at this diagram very carefully. If you see here, numerical aperture is defined as n into sine theta max, where what is n? N is the refractive index of the beam from where the light is entering. It is neither refractive index of core nor of cladding. It is the refractive index of the medium where the beam is entering from. Where it is entering into, it is entering into fiber core. All right. So if you look at here, the beam which is entering here, or with this angle the beam enters, for example, it is theta. So the maximum value of this angle, at that maximum value of angle, if light beam enters and if it goes inside the cable and undergoes repeating total internal reflection, then that maximum angle is called as acceptance angle. As its name suggests, acceptance, that much angle is only acceptable. Beyond this, if beam enters to the cable, look at the cursor, it will not be propagating. Why it will not propagate? Because it will not satisfy the conditions of total internal reflection, that is TIR. So if we determine theta maximum, that is the maximum value of acceptance angle, we can easily calculate numerical aperture as n into sine theta max. That is sine of maximum angle, which is acceptance angle here. So n sine of acceptance angle is actually numerical aperture. And why we are calling it as measure of acceptance angle? More is the acceptance angle, more is the numerical aperture, or vice versa. So this is the correlation between numerical aperture and the acceptance angle. Numerical aperture is the measure of ability of an optical fiber to collect or confine the incident light ray inside it. I have already explained, this is the ability to collect. This is the ability to capture, the capability to collect the light. How much light is allowed, and beyond certain angle, if beam is trying to enter, that light will not be confined, will not be collected by the fiber. So therefore, numerical aperture is also considered as measure for collecting capability, light collecting capacity, light collecting ability. Numerical aperture indicates. It also shows the efficiency with which light is collected inside the fiber in order to get propagated. This is very important, that to be propagated, the maximum efficiency with which light can be collected so that it is propagated inside. You can collect any amount of light, but that significant amount of light which gets propagated because it meets the requirement of TIR. So that much light and that much span, that angle is called as acceptance angle. So therefore NA, it also is an efficiency, how system is efficient, how much the light is getting collected and then getting propagated finally. When the light is emitted from an optical source, where do we get light from? When the light travels inside core, where do we get it? We get it from light source, that is optical source, maybe LED or laser, we'll study later. So the light is emitted from optical source, then fiber must be highly efficient so as to collect maximal emitted radiation inside it. The fiber optic material, the fiber which is capturing the light coming from optical source, must be efficient so that maximal amount of light gets inside it. We are using the term maximal because maximum may not be the appropriate term. Maximal means there is an optimum angle up to which light is allowed to enter. So the maximum amount of radiation, that goes inside the cable is, that depends on how fiber is efficient, how fiber efficient is. The light gathering efficiency of an optical fiber is the important characteristic while transmitting a signal through an optical fiber. This is an important efficiency. This is an important parameter in order to determine the transmitting capability of fiber, that is numerical aperture. See one diagram here. This diagram includes core material inside having refractive index of N1. Then there is cladding, that is outside core, having refractive index of N2. Both the sides, it means the structure is the cylindrical structure. The cable is cylindrical. So outside layer is cladding, which has refractive index of N2, where N1 is the refractive index of core. Now what is alpha here? Look at the diagram. Alpha is the angle at which light is firstly incident. Do not get confused with angle of incidence. Generally, angle of incidence we talk about inside the fiber in order to check if the TIR is satisfied or not. So this angle is the angle at which the signal is accepted, the signal is arrived. So what is that angle? Alpha. Then you see that since this material this material, that is core, has higher refractive index than this material, because this is refractive index. If core is a glass, it will have around 1.5, which is higher, so refracted towards normal. That's the rule of refraction. If the refractive index is lower, it will be refracted away from normal. If it is higher, it will be refracted towards normal. So it's coming towards normal here, and then you can look at here, then it's going and it's striking at point B. So AB is a path. A is the beginning point of the core where the light has entered, and B is the point where there is an interface between core and cladding. What is TIR condition? When the angle of incidence, this angle of incidence is greater than the critical angle. Look at critical angle has been shown here. What do we mean by critical angle? The angle of incidence at which the angle of refraction, you see here, if the angle is coming here, the light is that is incident at point B, so it will refract in the cladding area, because cladding also has lesser refractive index, and it is going away from normal, please remember. And when you increase this angle more and more and more, what will happen? This refraction angle will increase, and when the refraction angle becomes 90 degree at certain value of angle of incidence at the point B, so that angle of incidence for which the angle of refraction becomes 90 degree. So the light follows this surface, that is interface surface. This is called as critical angle. And for all materials, the critical angle is also considered as one of the parameter. So acceptance angle is the maximum angle through which light enters. This angle and NA are related to each other. We'll see it. And see here, this alpha determines. You look at here, if you change this angle alpha, this incidence angle will also change. Please understand. So if we increase this angle, what will happen? This will decrease. This particular will decrease. Why it will decrease? Because what will happen? This will go towards this side, and therefore the angle of incidence requirement will not meet. So there is certain value of alpha at which the light is entering, so that the incidence angle is greater than the critical angle of that material. What will happen? It will have TIR. The condition of TIR, which is called as total internal reflection, for the propagation of light ray comes into action only when most of the light is collected inside the fiber. How it will propagate inside the fiber? It will propagate inside the fiber when TIR, total internal reflection, happens or occurs at point B. When will it occur? It will have to meet two conditions. One, the critical angle must be less than the angle of incidence, and it must pass from higher refractive index material to lower refractive index material. So consider a light ray XA here, that is incident inside the fiber. The refractive index of core is N1 and the cladding is N2. So you can understand, if you increase the value of alpha, the angle of incidence will change, and if the angle of incidence changes, the path, the light which is either refracted or following this surface, or again going back inside the same material that is reflected inside the core, it depends on this alpha. So therefore the alpha is acceptance angle, maximum value which is allowed by which the light enters, and it has TIR. The X-ray is launched from denser medium to rarer medium by making an angle alpha with fiber axis. The angle is known as acceptance angle. The angle of incidence should be more as compared to the critical angle. We know that, so that the TIR happens. The angle of incidence must be greater than the angle of critical angle. That is critical angle. Otherwise, if the incidence angle is less, then the light will get refracted. Rather than reflected. the light will become refracted. And what is the condition for light propagation in optical fiber? TIR. So what TIR demands for? TIR demands for the angle of incidence must be greater than the critical angle. So if we write Snell's law here, do we know this interface alpha, here is the theta, and the refractive index is n here, which is actually 1 for air, and here the refractive index is n1. We know that there is a formula, Snell's law. Snell's law was suggested for the light which is entering from one medium to other medium, having two different refractive indices, and having the light having two different angles, angle of incidence and angle of refraction. So in this case, the refractive indices are n and n1 respectively, and the angles outside and inside the material are alpha and theta respectively. So what we can write using Snell's law, we can write n sine alpha is equal to n1 sine theta. What is next equation? Theta is equal to pi by 2 minus theta c. Look at the diagram. Here, theta, theta c, and there is a perpendicular again. So if you add 90 degree plus theta c plus theta, it will give you 180 degrees. So how can we calculate this theta c? This is 90 minus, these all three constitute together. Theta c plus theta will be 90 degree. So your theta c will become theta minus 90 degree. If you add theta plus theta c, it is pi by 2 radian or 90 degree angle. So theta can be written as pi by 2 minus theta c. If we substitute this, we'll get some expression. We'll come to next. Look at here carefully. So n1 sine alpha can be written as n sine alpha can be written as n1 sine pi by 2 minus theta c, which we can further write as n1 cosine theta c. And sine alpha can also be written as n1 by n cosine theta c. So cosine theta c, it can be written as, how can we write cosine theta c? It will be, cosine theta c can also be written as square root of 1 minus sine square theta c. Is it clear? So sine alpha, we are trying to get the expression for acceptance angle. Sine alpha can be written as n1 by n square root of 1 minus sine square theta c. Now the same expression, which expression? The Snell's law, which we have written here for this interface, that is n sine alpha is equal to n1 sine theta, can also be written at this point, that is at point B. How? n1 sine theta c is equal to n2 sine of what? Certain angle. But if the angle is theta c, what is angle in the cladding area? In the cladding area, the angle is 90 degree. So what can we write for an expression using Snell's law? N1 sine theta c is equal to N2 sine 90 degree, because at critical angle, the angle of refraction, that is theta 2 here in case of cladding, is 90 degree, and sine 90 is equal to 1. And therefore you look at here, N1 sine theta c can be written as N2 sine 90 degree. So N1 sine theta c is equal to N2, because sine 90 is 1. So what is value of sine theta c? Sine theta c can be written as N2 by N1. And when we substitute here, it becomes 1 minus N2 by N1 square. Look at here carefully. That is, here, that is cosine theta c is 1 minus N2 by N1 square. Sine alpha can be written as, look at sine alpha, that is N1 by N cosine theta. So N1 by N square root of 1 minus N2 by N1 square. When we solve it, N1 square minus N2 square, and N1 square will go outside, N1 will cancel, and we know that N is equal to 1 for air, if the medium is air. So what is sine alpha here? Square root of N1 square minus N2 square only. And what is the sine alpha? Sine alpha into N is the numerical aperture. Sine alpha into N, what is the expression of numerical aperture? numerical aperture is equal to n sine theta, where n is the refractive index of the medium from where the beam is entering into the light. And therefore, numerical aperture is equal to square root of n1 square minus n2 square. So it can be seen that numerical aperture depends, as we have noted in the beginning, numerical aperture depends on n1 and n2. What are n1 and n2? n1 and n2 are refractive indices. Do these refractive indices depend on the material composition, material design? Yes. If the material composition changes, the refractive index profile changes. We'll discuss different refractive index profiles later in subsequent lectures, in next lectures. So therefore, we have noted that when the composition of material changes, the numerical aperture changes. Numerical aperture is related to the design consideration or composition structure, composition factor of the optical fiber material. So this is the relation between numerical aperture and as well as the acceptance angle. Where is the acceptance angle? Acceptance angle is sine alpha, where alpha is acceptance angle and sine alpha is numerical aperture. So as the numerical aperture shows the light, it indicates the light collecting capability of fiber. Its value must be high. If we want more light to enter so that the strong signal can propagate, the numerical aperture must be as high as possible. So higher the value of Na, better will be the fiber. Higher the value of Na here, better will be the fiber. And if higher the value of Na, if we can write the value of alpha, sine alpha is Na. What will be alpha here? Sine inverse of Na. So what is the meaning? More is the numerical aperture, more will be acceptance angle. And therefore, higher the value of Na, better will be the optical fiber. However, greater value of Na will be achieved if we want larger value of Na. That can be obtained only when difference between the two refractive indices is high. For this, either N1 is to be very high or N2 is to be very low. You can see the expression here. N1 is square minus N2 is square. Actually, it's not the difference, because N1 square minus N2 square can further be written as N1 plus N2 into N1 minus N2. So when will the numerical aperture be high? We can say that N1 is very high, N2 is low. Because if both are very large, N1 plus N2 will be high, but the difference will be very small, but the ultimate product will be small. So therefore, the difference between N1 and N2 must not be very high. It should be low value, so that N1, and how it can happen, N1 is very high, N2 is to be low. So the difference will be larger. The difference will be larger, and if the difference is large, then numerical aperture will be high. More is the numerical aperture, larger is the acceptance angle. Larger is the acceptance angle, better will be the light collecting capability. Higher is the light collecting capability, better will be the optical fiber. So they all are interrelated. The only motive is not to have high acceptance angle, but also to propagate the accepted angle with minimal attenuation. Sometimes there is a constraint on acceptance angle. How much acceptance angle, how much maximum angle is allowed. Sometimes maximum angle can go beyond certain limit and still TIR is happening, but there is some attenuation of light which is occurring inside the while propagating the wave. So that has to be avoided. We have to allow maximum angle in such a way that the attenuation inside is minimum, so that the signal travels with high or strong intensity. There are several parameters which are taken into considerations for selecting the appropriate fiber for signal propagation. Therefore, there are a number of parameters, there are a number of selection parameters which are taken into consideration while selecting the fiber. Okay, so let's do one numerical problem. And I'm sorry, in step index, because we have not studied step in graded index fiber. There are two types of fiber: step index, graded index. As its name suggests, when we say step index, what do we mean by fiber? It has two components. What are two components? Core and cladding. So when you go from core to cladding, there is a change in refractive index. If the change is abrupt, for example, the core refractive index is 1.5, cladding is 1.2 or 1 suddenly. So there is sudden change, there is abrupt change. The change is not slow, the change is not gradual. It in the interface, if you cross to the next area, the refractive index suddenly changes. That profile is called as step index. Graded, the change when you cross from N1 to N2, change will not happen suddenly, change will occur gradually. So this is step index problem. We'll study step index and graded index fibers separately in subsequent lectures. So it has core refraction index of N1 given to you. The cutoff angle for light entering the fiber from air, the cutoff angle of the light entering the fiber from the air is found to be 8.5 degree. What is the numerical aperture of the fiber? What is the index of refraction of cladding for this fiber? If the fiber were submerged in water, if you submerge the fiber in the water, what would be the new numerical aperture and cutoff angle? So what is the first problem? First problem is what is the numerical aperture? Numerical aperture, how do you calculate? N0. N0 means that refractive index of the media from where the beam is entering. Sine theta max. And when this value is given as 1.0003, that is for air, it's almost 1. 1 sine of, and this angle is given to you. Look at here, cutoff angle for light entering. That cutoff angle is the maximum angle. So this is given to you as 8.5 degree. If you calculate, the numerical aperture comes as 0.148. That is the first value. That is the numerical aperture of fiber we have obtained. When the index of refraction of cladding can be found, how do we calculate? What is the refractive index of cladding? We know that numerical aperture we have calculated as 0.148. Now numerical aperture is equal to square root of n1 square minus n2 square. We know the value of n1. Now n2 can easily be calculated as n2 square is equal to n1 square minus na square. So we have two values, that is, I mean n2 square is this one. So n2 is 1.417, that is square root of that value. Okay, we will not take negative value because we know that it will have negative as well as positive. So we have what is refractive index of cladding, that is 1.417. Core 1.425. You look at here, difference is not big here in this case. So this is the problem. Now what is the next problem? We have calculated numerical aperture, and we have also calculated for that numerical aperture what is the refractive index of cladding. Now if the fiber is submerged in water, so what will happen if it is water? Now light which was entering earlier from air to glass, now it will enter from water to glass, and therefore n0 here, n water is 1.33, that is 4 over 3. The cutoff angle will have to change if the numerical aperture to be unaffected by NO. So numerical aperture, the cutoff angle will have to change if the numerical aperture is unaffected. Suppose we want, it says that what would be the new numerical aperture and cutoff angle. For this, we can calculate new numerical aperture and new cutoff angle. So sine theta max is equal to numerical aperture by N0. Numerical aperture is 0.14 that 8 divided by 1.133. So what is the new acceptance angle? Is 6.38. Acceptance sorry, the new acceptance angle is 6.38. Earlier it was 8.5. Earlier it was 8.5. Now this becomes 6.38 because as we have noted that the numerical aperture, acceptance angle, all these they depend on what are the factors on which they depend. They depend on the composition of materials, the refractive index, and the other things on which it depends. So this is a problem related to the concept of numerical aperture and the acceptance angle which we have studied. So let us sum up the lecture. What we have done today. Today we have discussed numerical aperture and acceptance angle. All right, numerical aperture is defined as n sin theta a, where n is the refractive index of that medium from where the beam is entering. And how do we calculate that numerical aperture is square root of n1 square minus n2 square. Numerical aperture can be high when the difference between n1 and n2 is large. So larger is the difference, larger will be numerical aperture. Larger is the numerical aperture. Look at here. More will be the acceptance angle. More is the acceptance angle, better will be the optical fiber. So in you know uh, uh, in other words, we can say that numerical aperture and acceptance angle both are the parameters which indicate the light collecting capability of fiber. All right, and then we have done one problem there. We have seen that when the light is entering from air, and in the next scenario, when the light is entering from water, then the acceptance angle and the numerical aperture both are changing. So this lecture is very important in a view of addressing or discussing the two important parameters which are used in order to understand the propagation of light, whether the light can be propagated or not, how much light can be propagated without attenuation or not, because in one place we have noted that how much angle is allowed. You have to allow that much angle so that the attenuation, the signal attenuation of light inside the fiber is minimum. Because if the signal is attenuated very too much, then the strength of signal will fade and the quality of signal received will not be, that SNR will be affected and the quality of signal received will not be good. So that's all for today's lecture.